Hello everybody, myself Jyoti and today we are going to discuss about shell model. So all of you must be aware about this binding energy per nucleon against atomic mass number plot, and this graph in nuclear physics is of utmost importance. Now here you can see that the binding energy, the elements which are having atomic number between 10, 20 and 180 approximately, they are having mostly the binding energy above 8 MeV. You can see here this value above 8 MeV. So they are stable. The light elements, the elements with the atomic mass number less than 20, they are light nuclei and they have a lesser binding energy per nucleon. And same is true for the heavier elements. Elements having atomic mass number above 200, mostly they are also having less binding energy per nucleon, and they are also unstable. Now, high binding energy for magic numbers. What does this mean? So the binding energy is unusually high if the number of neutrons or protons are equal to 2, 4, 8, 20, 50, 82, and 126. So what is binding energy? Binding energy, it is the energy which is required to keep the or hold the nucleons together inside the nucleus. Or in other words, we can also define binding energy as the minimum amount of energy which is required to break the nucleus into its constituent nucleons. Now here you can see in the graph there are certain kinks which are there. So these elements, now here if you take the example of carbon, nitrogen, oxygen, all of them, they are having binding energy per nucleon less than 8 MeV, but still they are found to be stable because either the proton number or neutron number for them, it matches with this one of this number 248. Like take the example of oxygen, 8 proton number, it is 8, so it is having exceptional stability. Again, you can take the example of Ce, which has Z equals to 58 and 8 atomic mass number is 140. So neutron number will be A minus Z, that is 82. The binding energy of Ce is found to be 8.35 MeV, which is approximately higher by 4 MeV as compared to its neighbors. So giving the discontinuity in the binding energy per nucleon versus atomic mass number curve. Now, what are these magic numbers? We know the numbers 248, but what are they and why are they called so? So, large binding energy means high stability, because binding energy, it is the minimum amount of energy which is required to break the nucleus into its constituent nucleons. Now, when I'm saying that particular nucleus has a large binding energy, that means if I have to break that particular nucleus, I will have to supply high amount of energy. That means that particular nucleus is highly stable. So large binding energy, that means high stability, and this unusual stability where neutron or proton number corresponds to one of these number 2, 4, 8, 20, 50, 82, and 126 is also reflected in a number of experimental facts. For examples, the if the proton number or neutron number, it matches with the magic number, this kind of elements, they are found to have more number of isotopes or more number of isotones. What are isotopes? Isotopes are the elements with same atomic number but different mass number. So suppose if you take the example of one of the element where the Z or N, it matches with proton, one of the magic number, in that case it will have more number of isotopes. Maybe it will have 5, 6, or 10 isotopes that way. Or isotones are the elements with the same number of neutron numbers. So it is true that it is also true in case of isotones that they will have more number of isotones. The numbers 2, 4, 8, 20, 50, 82, and 126 came to be known as magic numbers because for quite a long time they could not be understood. Physicists, they were not able to figure out why at this particular numbers they are getting some other kind of result. So that is how they named them as magic numbers. Now try to understand what is atomic shell structure. So physicists were familiar with periodicities existing in atoms because of the atomic shell structure. What is atomic shell structure? Atomic shell structure, it is the structure where we have a central nucleus and then electrons are orbiting around in different shells outside the nucleus. So physicists were familiar with this type of atomic shell structure, and also the dependence of various chemical properties depending upon the shell structure. Like for atoms, as experiments have been shown, there are marked discontinuities in the ionization potential at regular intervals as a function of the atomic number. So ionization potential increases as atomic number increases, but uh, or decreases, whatever, but ionizing potential, it has a discontinuity because we in between we have noble gases. So for neon, argon, uh, or a particular element where it has a it corresponds to complete filling of an electronic shell, in that case we get a marked discontinuity. So problem which was faced by nuclear physicists was that it was very tempting for nuclear physicists to devise nuclear model. So they wanted to build nuclear model similar to what we have atomic shell model. And they were thinking that as atomic shell model was able to explain chemical properties of the atoms, in a similar fashion nuclear model will help to understand nuclear properties of the atoms. However, this task is not at all straightforward, because when we talk about atoms, that for atoms there is a clear cut Coulomb force which exists between a nucleus and electrons. On the other hand, for nuclei, there is no obvious central attractive force in which nucleons might move. So we have a compact nucleus, and electrons, they have larger space to move in the orbit around the nucleus. But that is not true in case of nucleons, which are compactly packed inside the nucleus. Now the question was, can nucleons move freely inside the nucleus? There is another grave difficulty when one calculates the density of nuclear matter. If you will calculate the density of the nucleus, which is mass upon volume. So mass is the mass of total mass of proton and neutron, and volume will be 4 by 3 pi r cube, because nucleus, it is slight, it is mostly spherical. So 4 by 3 pi r cube, where r is nuclear radius, which is of the order of 10 raised to minus 15. So if you substitute all these values, you will get nuclear density of the order of 10 raised to 17 kg per meter cube. Imagine this value. This value is very, very high value, because density of water, that is also 1 kg per meter cube. Imagine that nuclear density, it is 10 raised to 17 kg per meter cube. This is a very high value, which makes it a formidable task to imagine that there is, the nuclear density is high, means nucleons, neutrons and protons, they are compactly packed inside the nucleus, and there is no space for these nucleons to move in different shells. Like electrons, they have lot of empty space in atom where they can move, but not, that is not the true in case of nucleons, like neutrons and protons, to move inside the nucleus. So what is a shell model? A shell structure of nucleus implies that nucleons move freely in nuclei, similar to electronic motion in atoms. That means, suppose when we take the atom, electrons are free to move. In a similar fashion, neutrons and protons, that means nucleons, they can move freely inside the nucleus. In other words, nucleons must largely move, and each nucleon, it is behaving, or its motion is independent of other nucleons. So Bartlett Guggenheimer proposed an independent particle model, which was called as shell model, for the nucleus in 1933, based on the analogy between atomic shell. So this approach leaned heavily on the analogies of the extranuclear electronic structure of an atom. They assume that each nucleon moves in an orbit similar to how electron moves in an atomic orbit, characterized by a definite angular momentum and a definite energy, and that it moves independently of other nucleons. This assumption is hard to justify in the light of large nuclear density. There is no space inside the nucleus for the nucleons to move freely, so it was very difficult to justify this. So failure of a shell model. So following the electronic shell filling process, Bartlett et al. Proposed closed shell of nucleons. He proposed on the basis of analogy. Each shell containing 2 into 2i plus 1 neutrons or protons. He gave this number also. This approach was able to account for only the first three magic numbers. So he was able to give explanation for first three magic numbers based on the shell model which he proposed. But later on, physicists lost interest in the shell model because of its failure to explain higher magic numbers, and no significant progress was made between 1936 and 1948 in developing this model. Success of liquid drop model. So perhaps the loss of interest of physicists in the shell model was also because of the another model which was proposed, that is liquid drop model. And liquid drop model was able to explain nuclear fission, which was a great success. So we have seen in the earlier lecture how a nucleus can be described in a collection of strongly interacting nucleons behaving in many ways like a drop of a liquid. And this model was quite successful in explaining nuclear fission and making predictions about variation of nuclear mass with A and Z. However, by its very nature, it was not able, or it was not capable of accounting for the discontinuities in binding energy at the magic numbers. So liquid drop model was also not able to give any kind of explanation for the magic numbers, and that is how physicists again got interested in using a shell model which can help in understanding the magic numbers. So Maria Mayer, in 1948, Maria Mayer forcefully drew the attention of physicists to the growing and compelling experimental evidence for closed shells in nuclei at the magic numbers, and attention was thus focused on the independent particle model or the shell model of a nucleus. Role of J.J. coupling. So in 1949, when Maria Mayer and independently Haxel, Jensen, and Suez devised a nuclear shell model which was able to account for all the magic numbers. Earlier, they were able to explain only first three magic numbers, but later on, they were able to account for all the magic numbers with the presumption of strong spin orbit forces for individual nucleons. Now, here they were able to do this because of the introduction of the J.J. coupling. In atomic and molecular physics, J.J. coupling was introduced, and that J.J. coupling concept helped for the developing nuclear shell model. So the introduction of the J.J. coupling was a very important step which resulted in a sequence of independent particle states matching the experimentally observed magic numbers, and that is how the shell model was developed. So what is the success of shell model? It gives the evidence of magic numbers which a liquid drop model couldn't give, and the angular moment of nuclei in their ground state. And failure of shell model is it cannot predict the excited state of nuclei and accounting for the degree to which many nuclei are non-spherical. So here this was just introduction about the shell model, how the shell model was developed. Later on, we will also in the next lecture we will also study what led to